Hello everyone. In this lesson, we will continue to study frequency domain analysis module of continuous system. Today, we will study the frequency domain analysis method of continuous system. We will review the main properties of Fourier transform and discuss their physical significance and engineering application. We have learned that Fourier transform is unique. The properties of Fourier transform reveal the internal connections between the time domain and the frequency domain characteristics of signal. The purpose of discussing the properties of Fourier transform is to understand the internal relationship of characteristics, to find the spectral density function of a complex function, and to understand how to apply them in electronic information and communication system. In this section, we mainly discuss symmetry, linearity, conjugate symmetry, scaling transformation, time shifting, frequency shift, differentiation in time domain, integration in time domain, convolution in time domain, and convolution in frequency domain. Let's start with symmetry. If the spectral density function of signal ft is fj omega, then formula 1 is true. When ft is an even function, formula 2 is true. This is symmetry. For example, the spectrum of the impulse signal is 1. According to the symmetry, we can find the spectrum of DC signal is 2 pi delta omega. Let's move on to the second property, linearity. It is so easy to understand this property. When a signal performs linear operation in time domain, in the frequency domain, its spectral density function also performs linear operation, as shown in formula 3. The third property, conjugate symmetry. Assume ft is a real function. If its spectral density function is fj omega, then formula 4 is true and formula 5 is true. That is to say, when the signal ft performs reverse operation, its spectral density function becomes the conjugate function of the original spectral density function. The fourth property, scale transformation. This is the key point of this class. For scale transformation, when the time domain signal ft is changed to fat by scale transformation, how does its spectral density function change? Here we can find that when scaling ft, its spectral density function satisfies formula 5. If a is greater than 0 and less than 1, at this time, the signal is extended in the time domain. From formula 5, we can find that its frequency domain is compressed. On the contrary, when a is greater than 1, the signal is compressed in the time domain. Its frequency domain extends to a times of the original. Here, we use waveform to express this scale transformation. In the case that a is greater than 0 and less than 1, Figure 1 shows a rectangular pulse and its spectrum. And the Figure 2 shows the extended rectangular pulse and its spectrum in time domain. In Figure 2, the spectrum are obviously 1/2 that of Figure 1. So in physical sense, as for scale transformation, the pulse duration increased to a times of the original. Frequency bandwidth of signal in frequency domain decreased to a times of the original. Obviously, its high frequency component decreased At the same time, its amplitude increased to 8 times of the original. Let's look at another case. When A is greater than 1, its time domain is compressed to 1/2 that of figure 1, and its frequency band is obviously twice of figure 1. That is to say, time domain duration becomes shorter and the frequency band is broadened. The high frequency component of the signal in the frequency domain increases. The amplitude of each component decreased to 8 times of the original. From this example, we can find that the duration of a signal is inversely proportional to the bandwidth of the signal. In X-ray engineering, especially when processing voice signals, in order to speed up the transmission of a signal, we need to compress the duration of the signal. But you should note that the cost of signal duration compression is to extend the frequency bandwidth. Next, let's take a look at time shifting. If the signal ft is time shifted, then its Fourier transform satisfies formula 6. Its spectral density function fj omega needs to be multiplied by an exponential factor. When it is compressed by modulus and phase, analyzing formula 6, we can find that after time shifting, the amplitude spectrum of the signal does not change. Only phase spectrum of the signal changes. We should also notice that when its phase omega t0 shifts to the right, it produces minus omega t0. When its phase omega t0 shifts to the left, it produces plus omega t0. After time shifting and scaling, you can get equation 7. Here is an example. If we know the Fourier transform of signal ft is fj omega, it conforms to the law of sampling signal. Find the spectral density function of f2t minus 5. First, transform the time domain signal. We scale it first and then do time shift. Because a equals 2 and the signal is scaled to twice of the original, so its spectral density function should be changed accordingly. After scale transformation, we should do time shift. It's clear that it should be time shifted 5 units to the right, so its spectral density function needs to be multiplied by an exponential factor. Here, you should note that because we have done scale transformation, so t should be time shifted by 5/2 units. Finally, we can get spectral density function of f2t minus 5. Let's look at the other method. Shift the time domain signal first and then scale it. First, we shift t 5 units to the right and multiply it by an exponential factor. Then we do scale transformation on it. The scale is 1/2. It is compressed to 1/2 of the original. Here we need to compress all of the spectral density function that have been time shifted. Then we can get its spectral density function. By comparing the two expressions, obviously the spectral density functions are the same. Let's look at the frequency shift. Frequency shift refers to if time domain signal ft is multiplied by exponential factor e to the power of j omega 0t or e to the power of minus j omega 0t. We can get formula 8. When performing frequency shift, you should know the plus sign and minus sign in the exponential factor and fj omega. Let's take a look at their waveform. This is the spectral density function of the original signal ft. This is the spectral density function after the original ft is shifted omega 0 units to the right. Obviously, the exponential factor is e to the power of plus j omega 0 t. The right graph shows the spectral density function after the original ft is shifted omega 0 units to the left. Obviously, the time domain ft is multiplied by e to the power of minus j omega 0 t. In engineering, frequency shift can be applied to the modulation, demodulation, and frequency division multiplexing of communication system. When we study frequency shift, there are two very important formulas you should master: ft times cosine omega 0 t and ft times sine omega 0 t. As shown in Formula 9, after time domain signal ft is multiplied by cosine omega 0 t, there appears frequency shift on the original spectral density function. When you use these two formulas, you should notice the difference between them. In practical engineering, frequency shift is usually used in spectrum shifting, modulation, and demodulation. Now let's look at differentiation. If a time domain signal ft performs first-order differential, its spectral density function satisfies Formula 10. That is to say, the original spectral density function is multiplied by j omega. As for the differentiation in frequency domain, if the time domain signal ft is multiplied by t, we can get a spectral density function jd fj omega over d omega. When you use this property, you should know that if there is a definite DC signal in ft, you should first solve the DC signal and then solve other parts by differentiation property. That is to say, first of all, you should first solve the Fourier transform of the DC component of ft, then according to differentiation property to solve the rest. Well, which field can we apply differentiation to? In complex variable function theory, it can be used to simplify the Fourier transform of time domain signals. In addition, in engineering, it is often used to solve differential equations in the time domain. This will be discussed later. Let's look at integration in time domain. There are two cases for integration in time domain. First, when big F0 equals 0, its integration in time domain satisfies Formula 11. When big F0 is not equal to 0, Formula 12 is satisfied. Formula 12 can be changed to Formula 13. Here, you should know big F0 means the value of fj omega when omega equals 0. According to the definition of Fourier transform, obviously it should be an integral of ft from negative infinity to positive infinity. That is to say, big F0 equals 0 means that the average value of ft is 0. In engineering, the average value of ft is 0 means that the DC component of ft is 0. Let me show you an example. Find the Fourier transform of unit step function. Here, if we want to use the integration to solve it, epsilon t and delta t have integral relation. The Fourier transform of delta t is 1. If we use integration, we can get the Fourier transform of epsilon t is 1 over j omega plus pi delta omega. Obviously, the dc of epsilon t is not 0, so pi delta omega appears in the solving process. Let's take a look at convolution theorem. Convolution theorem is divided into convolution theorem in time domain and convolution theorem in frequency domain. Convolution theorem in time domain means that if we do convolution algorithm on the time domain signal f1t and f2t, then a spectrum becomes a multiplication operation. That is to say, it satisfies formula 13. Convolution theorem in frequency domain refers to if time domain signal f1t is multiplied by f2t. In the frequency domain, the result becomes the convolution of f1j omega and f2j omega. Their convolution should be multiplied by 1 over 2 pi. Convolution theorem is also very important in practical engineering. We have learned the convolution theorem of continuous systems in the second knowledge module. If f1t represents the unit impulse response of a continuous system, f2t represents the input of this system, then the frequency domain characteristics of the input of the system can be hj omega times fj omega. We mainly discussed the properties of Fourier transform in this class, including symmetry, linearity, conjugate symmetry, scaling transformation and time shifting, frequency shift, differentiation in time domain, integration in time domain, and convolution theorem, which includes convolution theorem in time domain and in frequency domain. For these properties, you must master the relationship between the time domain and the frequency domain, especially understand their physical meaning and engineering application. This class is over. Thanks for your listening. Goodbye.